In this video, we're going to continue our discussion on polar coordinates and learn how to graph polar equations. And there's a lot of different ways to do it. Most just comes down to knowing how to plug in different values for theta, plotting some points, and connecting. However, we do also make use of symmetry of our polar graphs when it comes in handy. And there are some standard types of polar graphs that we can recognize by the equation. But first, let's just start by defining exactly what a polar graph is. So a solution to a polar equation is an ordered pair r theta that satisfies the equation. The graph of a polar equation is the graph of all solutions to the equation. So it's every single point r theta that satisfies the equation connected with a smooth curve. So let's do an example where we're just going to make a table of points and see what the graph looks like. So let's start by graphing r equals -4 cosine of theta. Well, let me just make a table of points for us, theta and r. And let's just pick some values of theta that are easy to work with. So for example, I'm going to start with theta equals 0. When theta equals 0, my r would be -4 times cosine of 0. Cosine of 0 is 1, so I get -4 for r. Now let's just plug in pi over 4. So pi over 4, when I plug that in, I'm going to get a square root of 2 over 2. Times my -4 gets me a -2 square root of 2. Do some other easy values. Let's do pi over 2. Cosine of pi over 2 is 0, so I get r is 0. And I can fill in a lot more. I'm just going to give us a little bit of an idea of what's going on. If I plug in 3 pi over 4, I'm going to get 2 square root 2. And just to get a better idea of how it finishes up, let me just plug in pi, and I'll plug in 3 pi over 2, and I'll plug in 2 pi. And of course, I could plug in other values, including our 5 pi over 4 and 7 pi over 4. But I'm just trying to get a rough sketch here. When I plug in pi, cosine of pi is -1. -4 times -1 is +4. When I plug in 3 pi over 2, cosine of 3 pi over 2 is 0, so I get 0. Plug in 2 pi, cosine of 2 pi is 1, so I get -4. So let's take a look at what this graph looks like. Now remember, when we're graphing in polar, you want to have some concentric circles with increasing radius. So that's like what we usually would have a grid for in rectangular coordinates. So there's 1, 2, 3, and 4, and it would keep going from there. And now let's plot our points. When I have an angle of 0, which is pointing over here in the direction of my polar axis, so to the right, I have an r of -4. That means I have to move in the opposite direction 4 spots, and I get this point over here. At pi over 4, which is this diagonal angle up here, I have -2 root 2. So I'd be moving in the opposite direction. Square root of 2 is like 1.4. And so I'm going to get something around here-ish. I'd have 2 times a 1.4, which is approximately a 2.8, so just around 3-ish. We'll put it right about there. It does not need to be perfect. Now, when I have an angle of pi over 2, that's sticking straight up, and I have r is 0, so that gets me a point right at the origin. 3 pi over 4 is this diagonal going over in the quadrant 3. 2 times root 2 is again just shy of 3. So approximately this point up here. At pi, I have 4. That lands back on this same point. 3 pi over 2, which would be 3/4 of the way around, I'm at 0 again. At 2 pi, which is back over at 0, I'm at -4. So you can kind of see I'm getting this circle. The orange circle right there, that is the graph of 4 cosine theta. And we would have a more accurate graph if I had checked values in between the ones that I did. You can just, the more angles you use, the more accurate your graph is. All right, so that was our first time graphing a polar equation. Now, sometimes it helps in polar equations to recognize if there's any symmetry, because then we can just find values of theta for 1/2 and then reflect to get the other side of the graph. So let's talk a little bit about symmetry. First, if replacing r theta with r negative theta results in the same equation, then the graph is symmetric with respect to the polar axis. Now remember, your polar axis is the horizontal axis. So this tells us if we replace r theta with r negative theta and still get the same result, then I can just find points for everything maybe from 0 to pi and reflect all of them to get everything from pi to 2 pi. 2. If replacing r theta with r pi minus theta results in the same equation, then the graph is symmetric with respect to the line theta equals pi over 2. Now the line theta equals pi over 2, that's our vertical axis. So if we find that our graph is symmetric with respect to that line, then we can find everything on the right half of the graph. So that's from negative pi over 2 to positive pi over 2, and then reflect everything to get from pi over 2 to 3 pi over 2. And then one more type of symmetry. Number 3. If replacing r theta with negative r theta results in the same equation, then the graph is symmetric with respect to the pole. So that would be similar to when we were doing graphs in X and Y being symmetric with respect to the origin. So you would get that by reflecting across the vertical axis and the horizontal axis. Now, in all three of these cases, it's very important to note that it says, if these things are true, then you have symmetry. But it does not say that if these things aren't true, then you don't have symmetry. If these statements aren't true, then we know nothing. The graph could still be symmetric with respect to these different types of axes or the pole. It just, testing it in this way was inconclusive. The reason for that is because of all the infinitely many ways we can represent our points, it might not be incredibly obvious doing these substitutions that you end up with the same equation. So you can use these tests to see if something is symmetric, but if it fails, that does not mean that it's not symmetric. It just means that, well, it still could be symmetric. We don't really know. Let's just graph and find out by looking at it visually. So let's do an example of graphing again, and we'll test for symmetry. And it's really a personal preference if you want to test for symmetry when graphing. It can save you a lot of time with your graphs, but it also could end up being a waste of time if all of these symmetry tests end up being inconclusive. So let's do an example. Let's graph r equals 3 plus 3 sine of theta. And I'm going to first check for symmetry, just so we can test these definitions. For the first type of symmetry, we have to replace theta with negative theta and see if we get the same equation. I would have r equals 3 plus 3 sine of negative theta. And then using our even and odd properties, I get 3 minus 3 sine theta. That's not the same equation, so this is an inconclusive test. We don't know if this graph happens to be symmetric to the polar axis or not. Second, replacing our theta with pi minus theta. That, using all my properties of sine, so our sum and difference formulas, would simplify to 3 plus 3 sine of theta, which is the same equation we started with. This means that my graph is going to be symmetric with respect to theta equals pi over 2. So it's symmetric with respect to my vertical axis. Let's check our third type of symmetry, replacing our r with a negative r. I would get r then is equal to negative 3 minus 3 sine theta. That's not the same equation, so it's inconclusive. It still could be symmetric with respect to the pole, but we don't know. So all we know for sure is that this graph is going to be symmetric with respect to the line theta equals pi over 2. So let's just go ahead and start plugging in some values and see what happens. I'm going to plug in various values from negative pi over 2 to positive pi over 2, and then reflect what I have on that right side of the graph. So I have a table of points, theta and r, and I'm going to start at negative pi over 2. Remember, our graph was r equals 3 plus 3 sine of theta. So at negative pi over 2, sine of negative pi over 2 is negative 1. 3 plus 3 times a negative 1 is 0. Now let me try negative pi over 4. Sine of negative pi over 4 is negative square root 2 over 2. So I get 3 minus 3 square root 2 over 2, which is approximately 0.8-ish. Just so that I have a better chance of graphing this, I wanted to estimate it. Now let's try at 0. If theta is equal to 0, sine of 0 is 0. So I get 3 plus 0, which is 3. And let's just do a couple more. Pi over 4 and pi over 2. At pi over 4, my sine of pi over 4 is square root 2 over 2. So I get 3 plus 3 square root 2 over 2, which is approximately 5.1 or so. And at pi over 2, sine of pi over 2 is 1, so I get 3 plus 3, which is 6. And now let's go ahead and plot these points and then reflect them to see what this graph looks like. So again, I'm going to make some little circles. There's 1, 2, I know I need to go all the way up to 6 for this graph, so I'm just going to keep drawing circles. 3, 4, 5, and 6. And so now there's my grid that I'm ready to graph on. Let's plot our points. So my first point was an angle of negative pi over 2, so that's pointing downwards with a radius of 0. So that's a point right at the pole. At negative pi over 4, which is this diagonal line, I'm at about 0.8. So not quite at 1. I have a point right about there. Now, at an angle of 0, I have my r is equal to 3. Angle 0 is going in the right direction, so 1, 2, 3. I have a point right there. At pi over 4, which is this diagonal up here in quadrant 2, I have 5.1 for my r. So that's 1, 2, 3, 4, 5, and a little bit more, so approximately right there is that point. And then the last point I did, pi over 2, is a straight up angle with an r of 6. So going all the way up to 6. And so I get the right side of the graph looks something like that. But now, remember we've had that this graph is symmetric with respect to our theta equals pi over 2 line. So I can reflect everything that I found over to this other side and get the other half of the graph. And it looks sort of like an upside down heart. Now, this particular type of polar graph, it's called a limacone. And this particular one is called a cardioid. There's a lot of different types of limacones, and this one's called a cardioid because it resembles a heart. So we have our lovely graph here of our 3 plus 3 sine of theta. It looks like an upside down heart. Now, in a graphing calculator, you can also graph polar equations. You just have to change the mode of the calculator so that you have polar graphs rather than Cartesian graphs. So you can always check your work using a graphing calculator. Let's do another example. These really just take a lot of practice. Graph r equals 1 plus 4 cosine of theta. And we're going to check for symmetry again to see if we can save ourselves some time. First, check for symmetry. Replace your theta with a negative theta. And see if you get the same result. Using the even and odd properties, I get r equals 1 plus 4 cosine of theta. So this one is symmetric with respect to the polar axis, which is my horizontal axis. 2. Replace your theta with pi minus theta. And then using my sum and difference formulas, I end up getting that this is r equals 1 minus 4 cosine of theta. That's not the same equation, so this is inconclusive. Remember, this means we still could be symmetric with respect to our line theta equals pi over 2. We just don't know if we are or not. 3. Replace your r with a negative r. And then if I solve that, I get r equals negative 1 minus 4 cosine of theta, which is a different equation, so this is inconclusive. So again, our graph could be symmetric with respect to the pole, but our test doesn't show us that it definitely is, so we don't know. However, since we got our first test to work and we know it's symmetric with respect to the polar axis, when I'm finding points to graph this, I can just plug in points from 0 to pi, and then I can reflect everything over the polar axis to get the bottom half of the graph. So let's make a table of points, just with theta between 0 and pi, and then we'll use our symmetry. So theta and r. I'm going to use theta equals 0, pi over 4, pi over 2, 3 pi over 4, and pi. That should hopefully give us enough to get a good idea. Now, when my theta is 0, cosine of 0 is 1, so I get 1 plus 4, which is 5. When theta is pi over 4, cosine of theta is square root 2 over 2, so I get r is 1 plus 2 square root 2, which is approximately 3.8. At pi over 2, cosine is 0, so I just get 1. At 3 pi over 4, my cosine is negative square root 2 over 2, so I get 1 minus 2 root 2, which is approximately negative 1.8. And at pi, my cosine is negative 1, so I get 1 minus 4, which is negative 3. So I know I'm going to need up to 5 for my circle. So 1, 2, 3, 4, and 5. And now let's plot our points on here. So I have 0, 5. That's going to be the point out here at 5 with an angle of 0. At pi over 4, my r is 3.8, so that's going to be just before 4. Pi over 2, I'm at 1. At 3 pi over 4, I'm at negative 1.8. So 3 pi over 4 is this angle, and I need to move in the negative direction, 1.8, so just shy of 2. And then at pi, which is all the way over on the left side, I have to move in a direction of negative 3, so I go 1, 2, 3 backwards, and I'm over here. When I connect those dots in the order that I graphed them here, we get something that looks sort of like that. But now I need to do all my reflections. So when I reflect this point over my polar axis, it's still exactly where it was. For this guy, I'd be down here at about 3.8. This guy's down here at negative 1. And that one, I'm up here at about 1.8. And when I connect all of those as well, that was not very smooth curve. Remember, these are supposed to be pretty smooth. I get that sort of shape, which it's kind of like a loop and it has another loop inside of it. So to make it a little easier to see, I'm going to erase some of my grid so that you can really see the shape of the actual graph. So I get that sort of shape over there. And what this one is, it's another limacone. But it has a loop. It has this little extra loop on the inside. So I'm sure you can see the graphs of polar equations tend to be very curvy. Lots of loops, circles. There's not sharp corners going on, which helps when you're trying to connect the dots, when you know they're going to be nice and smooth. Let's do another one. Let's graph r equals 3 sine of 2 theta. Now I could check for all my symmetry. I'm going to save us a little time and tell you that when I checked for all the symmetry on this one, I got that it was all inconclusive everywhere. So we're not going to be able to use the symmetry to help us too much. But that's okay. We'll try some other things. I have, let's just make a chart. And let's plug in a bunch of values between 0 and 2 pi. So I just like to use counting by pi over 4s. That usually gives me enough to get a general idea of what the graph looks like. So I'm just counting by pi over 4s all the way around. And we'll see what we get. When I plug in 0, I'm going to get 0. When I plug in pi over 4, I end up getting 3. 0, negative 3, 0, 3, 0, negative 3, and 0. So I know it's going to go all the way out to 3. So let me just put my circles like I've been doing. And let's get ready to graph this guy. Now it's a little strange trying to figure out how this is going to work. Starting at 0, and an r of 0 is right here in the origin. Pi over 4 with an angle of 3 is up here. And then at pi over 2, which is my vertical angle, I'm back down at 0 again. So I kind of go from here, make a loop, and come back to my point. Now let's see what happens next. At 3 pi over 4, which is my diagonal in this direction, I'm at negative 3. So that's down here. And then at pi, I'm back at 0. So again, I go out to that point and then back, and I've made another loop. 5 pi over 4 is my diagonal down here. I'm at 3. And then at 3 pi over 2, I'm back at 0. So again, I have another little loop. 7 pi over 4 is my diagonal in the 4th quadrant, but I have a value of negative 3. So that's in this direction. And then I go back to 0 again. So I get another loop around. And so what we end up with is just what's in the orange there. Let me erase my guidelines for my grid. And what we have is something that kind of looks like a flower. So there's our graph right there of 3 sine of 2 theta. And I said it looks like a flower, and it's actually named after a flower. This is called a 4-leaved rose. And as you can imagine, there's going to be a lot of different types of roses. It all depends on how many petals or leaves they have going around. So let's just talk in general what some of the most common types of polar graphs are. Just so that you have a better idea of what you should be getting when you're graphing. One thing that we tend to get are just straight lines. your straight lines are going to look like either theta equals 0, which gives us the x-axis, theta equals pi over 2, which gives you the y-axis, theta equals some number a, that's just a line through the origin, and it can have all sorts of different slopes. You can also have equations that look like a over sine of theta. That's a horizontal line. Y equals a. Or we could have r equals a over cosine of theta. That's a vertical line. X equals a. So these are all different examples of what a straight line would look like in polar form. And of course, you don't have to memorize all this because you can always plot points and figure out what the graph looks like. So lines are something that happens quite a bit. Another very common thing is getting circles or spirals. So something that makes a circle is r equals a. This is a circle with radius absolute value of a, and the center is at the pole 0, 0. Another example of a circle is r equals a cosine of theta. This is a circle that has a center on the polar axis and has a radius, absolute value of a over 2. So that's going to be a circle, but it's going to have its center somewhere on the horizontal axis. So it could be perhaps a circle appearing over on this side. Something like that. All depends on the value of a. We can also have circles that look like a sine of theta. That's a circle with the center on the line theta equals pi over 2, and again has a radius of the absolute value of a over 2. So that is a circle where instead of being like on the right or the left side, it's going to be up on top or up on the bottom or down on the bottom. So it would look something like that. So those are all the circles, and then a spiral. Your spiral equations look like r equals a times theta. That makes a spiral. And so those ones look something like, just like that, going on forever, continuing to spiral around. Now, of course, another very common type of graph to get is our limasones. We've already had a couple of those showing up. So all of the limasones look like a plus or minus b cosine of theta, or a plus or minus b sine of theta. And then just depending on if a is bigger than b or equal to b, you get different types of shapes. If a is less than b, you get the loop in there, like one of our previous examples. So if I have a less than b, we get a loop with it. Those are the ones that look something like that. If a equals b, you get your cardioid. We had one of those earlier too. Those are the ones that look like a heart. Then some slightly more complicated ones if your A ends up being smushed between B and 2B, you get what is called a dimpled limacone. And those are kind of strange to draw. It's sort of looking like a cardioid, but not quite heart-shaped. It's more like kind of a circle and you're kind of punching it in a little bit, so it dimples in a little bit, but it's not quite a heart shape. And then if you have A greater than or equal to 2B, you get what's called a convex limacone, and that it kind of ends up flat over on that side where it was dimpled before. That's not a very good picture of it, but it just gets flatter and flatter there. Now, another type of common graph are our roses that we just had an example of. So your roses are of the form A cosine of n theta or A sine of n theta. And there are n petals if n is odd, and there are 2n petals if n is even. So you're going to have those flower-shaped graphs, and the number of petals depends on what that number is inside of your sine or cosine function. And one last really common type of polar graph looks sort of like a figure 8. They have the form r squared equals a squared cosine of 2 theta, or r squared equals a squared sine of 2 theta. Both of these look like a figure 8. For cosine ones, they are symmetric with respect to the polar axis. So you're going to get a figure 8 that looks sort of like that. Wow, that's a terrible drawing. There we go. And that A that we have in here is how far out the maximum distance is. And for if we have a sine in the equation, it's going to be symmetric with respect to theta equals pi over 4, which is a diagonal. So those ones look like a figure 8 going that way. And again, the biggest point out here is at A and the angle pi over 4. So that's where that A comes into play. So let's do just 2 more examples of graphs. And we're going to just see what some of these different types of graphs look like. So for example, if we graph r squared equals 25 cosine of 2 theta, I know this is going to look like a figure 8, and it's going to be symmetric to the polar axis. And I know it's going to go all the way out to 5. So I know that the graph is going to be some form of a figure 8 that goes like that out to 5. And I knew that just by looking at the form of the equation. Now, of course, we could just plot points and you would get the graph the same way, but this saves us a little time if you're familiar with what some of the standard formulas look like. Our last example, let's graph r equals 0.8 times theta for theta greater than or equal to 0. Now, I know that this is going to be a spiral, but that's all I know is that it's spiraling around. I don't know anything else. So I'm going to make a couple of points just to make it a little bit easier to graph. Let's use 0, pi over 2, pi, 3 pi over 2, and 2 pi, just to get us an idea of what this spiral is doing. When I plug in 0, I get 0.8 times 0, which is 0. When I plug in pi over 2, I'm going to get 0.4 times pi, which is approximately 1.3. When I plug in pi, 0.8 pi, which is about 2.5. When I plug in 3 pi over 2, I get 1.2 pi, which is about 3.8. And when I plug in 2 pi, I get 1.6 pi, which is about 5.02, just to get us an idea. And now let's graph this guy. I know I need to go out towards a little bit after 5. So 1, 2, 3, 4, and 5. But it's so barely after 5 that should be good enough to get an idea. Now let's graph this. I have 0, 0. My next point is pi over 2, my vertical angle, and about 1.3. At pi, I'm over at 2.5. 3 pi over 2, which is going down, I'm at 3.8, so just shy of 4. And then over at 2 pi, I'm out just past 5. And I get connecting, knowing it's a spiral. It's going to keep going around that way, and I have my orange spiral. And again, I'm going to erase my grid line so you get a better view without the grids distracting you from what the spiral looks like. Let me clear that up. And then you see that spiral shape, and it just would keep going from there. So that's all I have for you today. Polar graphs take a lot of getting used to. It's just a lot of plugging in points and connecting the points smoothly. It helps when you're a little more familiar with some of the standard types of graphs, but you can always create a table of points regardless to get the pictures. A lot of them are kind of fun to draw. You get a lot of loops all over the place. They're kind of pretty. So you might want to try out a few examples on your own just to see all the different types of graphs you can get. If you have any questions, feel free to drop them below. If you're a current student, you can also ask in office hours, email, or in class. And I'll see you guys next time.